not a decentralized service, but it's like a federated type of Twitter. Maybe it will be decentralized later. So the Polkadot project, it's mostly being developed right now by Parity technologies. As Michael said, you might know them as developers of one of the main Ethereum clients that runs the Ethereum network. But the project is also being supported by the Web3 Foundation, and hopefully the Polkadot will be built not only by Parity, but also by other teams in the future. So a little bit first about the Web3 Foundation. So in general, Web3 is this concept, especially that emerged in relation to decentralized technologies in the beginning of Ethereum. So it's basically the foundation will be trying to support all the different technologies that might be contributing to this vision of Web3, so decentralized web. So one of those technologies, is Polkadot, but there are also other technologies such as like DAO or software and publication, data publication platforms like IPFS that the foundation will be supporting, and it won't be developing anything in-house, just supporting different teams that are contributing to the vision. So maybe something like Mastodon, or maybe something like Riot, which is a decentralized communication system. So the foundation is interested to get in touch with as many people as it can that are interested in the Web3 vision. So if any of you are interested, get in touch. But most of the talk, I'll be talking about the Polkadot project itself. So recently, we have been seeing that there is many different chains appearing. So some of them are public chains. So for instance, there is Zcash, there is Tezos, there is a lot of different chains in the public sphere. And some of them are consortium chains. So enterprise is starting to want to use blockchains, but maybe they don't want to use the public chains because of different reasons, and they are making new chains that are run in between a number of organizations. So maybe an energy chain or chain related to finance sector. So in general, their motivations are very varying. So some chains introduce some new privacy features. So something like Zcash. Or some consortium chains as well, because the state is not visible publicly to everyone. That's why they are used by the consortium. Some chains introduce, make it easier to do smart contract formal verification, or at least claim to do so something like Tezos. Some chains might make it easier to make light clients for them. So for instance, for Ethereum, it would be a fairly difficult task to make a mobile client that is fully featured, because it would either require a lot of, a light client requires lots of bandwidth, or a full node requires lots of resources locally. Some chains are domain specific, so something like a Waves chain is very focused on tokens. It makes it easy to issue new tokens, make sales, and doesn't really care about too much of the smart contract business, but it's very easy to use for the particular case that is being used for. And some other chains, especially consortium chains, might introduce completely custom fee structures. So maybe if there are some electric car charging poles on a blockchain. We don't want those charging poles maybe paying the same fees every single time as a regular user, because maybe they have very predictable behavior, and it's very unlikely that they will, for instance, spam the network, as opposed to a random person that joins the network, and possibly they should be charged much more. While on the public networks, such as Ethereum or Bitcoin or any other public network, there is no real differentiation between the users, while consortia might want to differentiate between different users. So in general, all of those different features that I was talking about can be split up into two different categories. So some of them introduce new features or somewhat that are work in different ways, so enable different types of things, and some things just enable higher throughput or lower transaction fees, and both of, but at the same time, introducing all those different new chains that introduce this extensibility and somewhat scalability, because now with many chains we can process way more transactions. We run into a number of different issues. So first of all, those chains, each of the chains need to be separately secured. So for instance, when Zcash was created, they had to gather up a completely new community of miners that would secure it, while Bitcoin is already very secure, or Ethereum is very secure, but Zcash then couldn't leverage any of the existing security of other chains. Or if someone makes a new proof of authority network or a new kind of a private or consortium network, they also need to make sure that there is enough nodes securing that particular network. And the more chains we have, the less secure each part of the system is, because people are basically spread across all those different chains, and we cannot provide all of them the same security. Second of all, it's pretty difficult to iterate because it requires a big effort to introduce the security to the chain and set up the consensus process of a particular chain. So maybe if it's a proof of stake chain, then issue some sort of staking token, make us sell that staking token or do something with it so that it actually becomes valuable, and then only then we can experiment with a new type of chain. And it fragments the ecosystem. So when Zcash is out there, on the Ethereum network, when we have our smart contracts, we cannot make our smart contract make use of any of the functionality of Zcash. It's a completely separate world. We might try to build some solutions kind of that interact with both chains, but those chains cannot directly interact with each other. Or again, the consortium chains that people are building, they are completely separate worlds. They cannot make use of any. Let's say there are degree certificates being issued on the Bitcoin blockchain, and now there is some consortium chain that wants to maybe check people that are joining the chain, and they want to check a certificate that is on Bitcoin. They cannot do that. So we need some way to pull the security of all the different chains that are out there, so that each new chain can enjoy the same security as all the other ones in the ecosystem. And we need some way to provide trust-free transactions, so transactions that do not require some centralized party to relay them between chains, and potentially arbitrary transactions. So not only token transfers, but again, we are talking about things like identity, where we have to check someone's identity on another chain, or we might provide some proofs. Maybe some proofs can be taken from a Zcash-like chain onto Ethereum, and this requires general trust-free transactions. And hopefully Polkadot can provide some of those two things that I mentioned. So currently, the reason that this is very hard to achieve is because the two disparate things are locked together. So when we look at the blockchain, we can think of it as two different pieces. So one is the state transition mechanism. So in the case of Ethereum, that would be governed by the EVM. So each transaction would transition the state according to the rules of the EVM and a number of different rules. And they basically say which transactions are valid, which transactions are invalid, which state transition is valid, which state transition is invalid. But this doesn't give us a unique history, a unique ledger of a particular for a particular blockchain. We still need to pick what is the single canonical history. So this is the issue of double spending. Maybe it would be valid for me to make a transaction and pay one person $10 and it would be valid for me to spend to another person $10, but it might not be valid for me to spend both of those at the same time. So I need to pick either one of those, and only one of them can be valid. So the process of picking amongst those all the valid potential histories of the blockchain or of this ledger is the consensus mechanism or canonicalization mechanism. So how do we canonicalize only single history? And those two things are coupled usually. But with Polkadot, the idea is to decouple the two. So basically, there is the validity is checked separately from canonicalization across the different chains. So different chains, different so-called parachains that are running in parallel, they have their own unique state transition logic that is being validated by a number of parties. And then once there is some set of valid potential state transitions, then there is the relay chain that arrives at a canonical set of state transition across all the different parachains. So usually something that is very heavy to compute is ensuring that everything is valid, but something that on the other hand shouldn't require that much computation by itself, but requires lots of communication amongst nodes is the canonicalization. So by splitting the two, by not requiring all nodes to perform this heavy computation, but at the same time not having all the nodes communicate with each other to achieve consensus, we can achieve those two things I was talking about. Pooled security and trust-free transactions are a bit separate. One second. Oh, get some water. So. So this enables us to have lots of different state machines. So basically, I was talking about at the beginning about the different blockchains, so something like Ethereum or something like Zcash. In reality, we don't really care what sort of consensus algorithm they are running that much. What we care about is their characteristics. So they both, in this case, run proof of work, and it's fine. It chooses the one canonical version of that particular chain. But what we really care is about characteristics of those chains. So what sort of state machine do they run? On Ethereum, I can write contracts, and on Zcash, I can have those private transactions. So now we can have a number of those different state machines. Maybe some of them are private, some of them are public, and they can all run together. And we can have, on the other hand, this consensus that is not split up amongst all the parties, but we can have it all done together. So in this case, it's a proof of stake consensus that ensures that all the different state machines that are being canonicalized by that consensus share the same security because they are canonicalized. Really, the security of canonicalization. Because the attacks, for instance, in Bitcoin, how you can attack Bitcoin is to make another history that is also valid, but is an alternative to the current canonical one. So really, the security is making sure that the canonical chain is never reverted. While in the current situation, it's split up. So what does the Polkadot, what types of chains it can connect? So Of course, it can connect the state machines that I was talking about, so new public chains. So we can make new chains that behave exactly like Ethereum or like Zcash or like Tezos or like some other chain. But it could potentially also interface with existing chains. So something like Ethereum or Waves, there could be a particular, so basically for each parachain, we can perform any sort of logic that links it to the Polkadot network. With new public chains, it would be this full state validation logic, so fully checking where all the transactions actually okay, and is the state transition correct. But for existing chain, it might be only checking a particular part of the state that is relevant to Polkadot network, but at the same time not relying on the consensus of the Polkadot network, because those chains already have their own consensus. So we can opt out of the consensus of the Polkadot network. And we can also connect consortium chains, so chains that are run kind of in private, but are represented by a set of authority nodes or members of a consortium. And it then enables all those different chains to interact with each other. So using those trust-free transactions, because the consensus is done simultaneously across all of them, we can then relay messages across all of those different chains. It makes it easier to experiment with different chains, because we can kind of plug in new chains by just saying, by just describing what's the new state transition logic of a particular chain, and plugging in a little bit like deploying a smart contract. And then it can run straight away and have all the security of the whole network, and potentially also migrating between chains. So a problem, for instance, now when we want to make some upgrade to a network, let's say like a Bitcoin network wants to make an upgrade, you need to decide between splitting up the network or trying to persuade everyone to be on the same board. But in this case, you could basically move into having two different parachains that are still connected together, but are running according to different rules. And if someone wants to stay on the old one, they can stay on the old one. If someone wants to move to the new one, they can move to the new one. But they can also slowly move to the new one, let's say, because we can have both of those parachains working at the same time. And because there are those trust-free transactions, everyone can migrate at their own pace. Yeah, and hopefully it enables a number of different applications. So so we might have again one parachain that enables private transactions, like a Zcash parachain, and then maybe you can then anonymously deposit something on an exchange by going through that parachain onto another parachain. Or you can look something up on a consortium chain. Maybe there is a consortium of universities where they are issuing degree certificates, but would you want to make use of this information on the Ethereum chain? Then you can potentially look it up. The consortium can keep running their chain as they're running right now, not worrying about the public chain that much, but you can expose certain capabilities to the public network. Yeah, and this is one particular flow where you use the Ethereum chain, you use a private banking chain, use some asset management chain that has its own characteristics, and each of those chains can be particularly well suited to the particular application. So maybe with the banking chain, certain again, maybe automated like ATMs can have transactions that are pretty much for free because we can check the hardware of the ATM and make sure that it won't be performing a Sybil attack on the network. There can be, of course, some sort of fail-safe, but the banking chain can be kind of very well suited to its application. Ethereum can be well suited to its application. At the same time, all of them can run transactions in parallel, which makes it possible to have many more transactions being processed than currently. And just to quickly mention how this compares to other multi-chain solutions, I think that a lot of them are missing either one of them or usually multiple of the different factors. So some of them connect the chains, but then they don't ensure that the security is pulled across all the different chains, which again leads to this issue where there is many chains. Then each of them becomes less and less secure because the community is spread out, and there is no single securing community over a chain of all of them. They often limit the types of transactions that can be relayed, so maybe limit them to ERC20 tokens or some sort of simple token that can be issued across chains, while we might want to have rich data and run any sort of programs across different chains. As we've seen it with smart contracts, it's sometimes not only about tokens. Sometimes they rely on trusted relaying, so some party sitting in the middle and like putting stuff from one chain across to another chain, and then the contracts cannot really rely on the message getting there and maybe being returned back to the original chain. Or they often impose very strict rules on how each parachain should look like. So what sort of consensus it should run. Maybe it should run only Tendermint, or maybe it should only run a particular type of state machine. So then it's more like, this is more something like sharding is such a solution where it's kind of homogeneous. All the state machines are the same, which is also very useful, but it's good to have flexibility to make it possible so that there are other state machines. So now, that was already a bit techy, but I will go a little bit more about like how Polkadot works. So as I said, right now, all single chains kind of just process transactions in series. While in Polkadot, there is this element where all the state machines are validated in parallel, and then there is this moment where once the validity of all the different parachains that are running in parallel is verified, then there is this moment of consensus amongst the validators, which ensures that there is a agreed upon state at particular points in running of all those different parallel chains. So this is achieved by having those different parachains. So parachains are those different state machines and that run in parallel. So maybe some are kind of more loosely coupled, like Ethereum, which has its own consensus mechanisms, or are more tightly coupled. And those more tightly coupled parachains rely on the relay chain to provide the consensus. So and basically you can think of parachains somewhat as currently running chains, but at any single point there are multiple possible chains running in parallel. While at some points in the running of the network, the relay chain gathers up all the different state transitions and makes sure that there is only a single one canonicalized from each of the parachains. The relay chain only provides the consensus and governance functionality. It cannot run like normal smart contracts or cannot do anything beyond just providing this consensus. And it also contains validation logic for all the different parachains. So basically, when a validator needs to determine if particular state transition is valid, they will look on the relay chain, take the particular state validation logic, run it on top of that state transition, and then see if it's valid or not. And all of that logic is stored on the relay chain. This state transition logic can be any this validation logic can be anything. So it can be either, again, a full state validation. So something like, yeah.
So is it kind of like merge mining? Like between the neighborhood or something?
Yeah, in some way. So in this case, in this case, it's kind of the opposite of that. The actual validation is done separately for all the different chains. So you are not processing multiple chains at the same time. So each parachain has its own community of collators that are doing the validation. Yeah, I guess in some ways that you are processing multiple chains, but in this case, the chains are processed in parallel. So merge mining is kind of opposite, has an opposite effect. It kind of tries to conflate two chains together in order to kind of share the security. So maybe the conflating on the consensus level is similar, but actually the validation is done in parallel rather than in series, like merge mining. But it can be also completely different logic. So it can be logic that checks different public chains. So maybe like Ethereum chain. So maybe that's a little bit like merge mining. Or it can be only checking, for instance, signatures. If it's a proof of authority chain, and all the consortium members said that this state transition is good, then validators just check all the signatures of all of the authorities, and then they say, okay, this state transition is good, rather than do full validation. So this it can be anything that one determines is good. And there are a number of different parties that are contributing to this ecosystem and make it all run. So first there are collators. So on each parachain, so this chain that runs in parallel has its own community they are a little bit similar to miners. And collators basically gather up all the transactions from the network. So now, similarly to Ethereum, there are miners sitting there on the network, listening to transactions and gathering them up in their transaction pool, and then trying to create new blocks. And the same for collators. But collators, instead of then releasing those blocks and hoping that they will become final blocks kind of straight away, they send those blocks off to validators. So there will be multiple collators on a particular parachain, and they will be creating multiple alternative histories of the particular parachain. And they need to run full nodes. So if I'm sitting, let's say, on an Ethereum-like parachain, I need to run a full node because I need to be able to validate the state transition and know everything there is necessary to validate the state transitions. But then what they do is they provide a light client proof, so basically a proof that doesn't require running a full node to validators. And then validators do not need to run the full node for each of the parachains. Then they only check get this proof, get the logic from the relay chain, and then run this logic on this proof, and then it outputs either this is a good state transition or it's a bad state transition. So this makes it possible to have lots of different chains that are where collators run full nodes, but no parties needs to run multiple full nodes. So this enables validators to perform much less work in order to ensure that the state transition is valid. And then there is a limited set of validators that then come together and form a consensus across all the different parachains. And then there are also those parties that are nominators. So the consensus process requires lots of communication. The more parties there are, the harder it is to come to consensus. So in case of something like Tendermint, there are multiple messaging rounds between all the validators. And the more validators there are, the number of messages explodes. So there are other consensus mechanisms that don't require such a high number of messages, But in general, the more validators we have, the harder it becomes. So we want to limit the number of validators so that they can come to consensus fairly quickly. But then in order to still distribute the power over what's going on, there is a number of nominators that run a particular function and look at the validators and then dynamically readjust and basically pick the validators that should be performing the validation. So it's a bit akin to delegated proof of stake, but it has a number of differences. So they are compensated in a few different ways. So the validators and nominators is mostly via just issuance of the token, so a little bit like Bitcoin or Ethereum, but also any sort of messages that finalize different chains or in any way not follow the protocol can be reported for a fee or for a reward. And collators, it all depends on a particular parachain. So they're a bit like miners. So they are gathering all the fees for a particular chain. Maybe if it's a consortium chain, the collators might be doing it completely for free because those are actually the banks that are also making use of the chain that they are running. So they might be willing to run collators for free. And then transactions on that chain might be potentially free or limited in a different way than paying for them. But they also can report other collators for providing invalid proofs because they all run full nodes and they are able to do this checking. So in the paper it was called fishermen, but the fishermen are kind of embedded in both of those roles. Yeah.
Does that require the Parachains to have like an extension to their own protocol in order to include fees for collators?
Yeah, so this would be part of the state transition logic, would have to include some reward for the collators.
So a parachain is not an existing chain, it's an extension to an existing chain, like Ethereum, for example?
Yeah, okay, so in case of something like Ethereum, the mechanic would be a bit different. So in this case, the collators might be incentivized by interchain messages, for instance. So it all depends on a particular parachain. So if there is some activity that should be metered, then yeah. And then then there is the consensus. So we have this validation across those different parachains. But then all the collators perform the validation of the particular parachain, but then we also need the validators to check, at least subset of the validators to check if particular proposed block is valid from a parachain. And then we need them to also vote on the availability of a particular block. And basically, they hire the availability, so like, does everyone actually see the block, or is it just one person saying that it's valid and no one else can even see the block? That determines that the higher the availability, the more likely it will be to be included in the relay chain. Then there is the relay chain has economic finality, which means that basically after a while you can be certain that all the transactions in all the different parachains are final and cannot be reverted, and the same goes for any messages that have been issued. And it relies on proof of stake to secure the network. So the validators need to be bonded. And this consensus can be also decoupled. So there might be a consortium chain that runs its own internal chain state machine that no one knows about what's going on inside. And then there is this set of authorities that manage the validation and any access control. So maybe when the messages should be relayed to other chains or not. But then still, Polkadot network could provide the consensus. So figuring out what sort of version of the valid state transition is being picked as a canonical one. But then there can be also a mechanism for kind of going in and out. So maybe if a consortium chain, suddenly all the authority nodes maybe are too collocated, there can be a fail-safe mechanism where the consortium chain starts relying on the Polkadot network if there is not enough authority nodes on the consortium network.
So what if like the block line time on one network is like much longer than on the other network?
Yeah.
So Peter, can you repeat the question?
Yeah. What if the block time for the chain is much longer than the relay chain, or the other way around? Yeah. So then it becomes a little bit more like a state channel, where basically like it's the easiest if it's in lockstep, but then especially if there is some authorities present, then they could just offload it from time to time. So there could be like two valid histories going on, and then it can be canonicalized after a while. So it depends really on the particular case. So one potential thing that could be done is let's say if something like Tangle or IOTA works, then it's a very different system. So it's based on a DAG rather than on a blockchain, and kind of each transaction confirms a few previous transactions rather than kind of having blocks of transactions. So it's a very different system, but potentially, if it works, then we might want to connect it also to other chains. So then this logic will be kind of much more complicated, and potentially we could, for instance, then embed a number of authorities within the Tangle, and then basically based on the determination of those authorities, what is the current state of the Tangle, kind of simulate a blockchain out of it and put any messages onto the Polkadot network. So this logic can be as simple as checking just signatures, or as complicated as you want it to be, and it's really up to the validators if it gets added or not, and it has to be appropriately measured, metered as well, because you cannot have validation of a particular chain take too long. So it's still a limitation. So that's how we arrived in this picture. That's in the Polkadot paper that has a number of that has all those different elements together. Here, the fishermen are pointed out as something separate, but they are really the same as collators and validators. So we have this relay chain that is relaying the messages across. So there might be something like the Ethereum chain, and then there is some bridge, and then the message can be relayed to some other chain. There are collators. So each kind of parachain has its own community of collators, and then validators are on each block. They are kind of split up into subgroups that determine validity, and then they come together to form a consensus around the relay chain. Something interesting that we are thinking about is how do we put in second-order relay chains or further order relay chains to kind of make it spread out even more and connect even more chains together. Yeah. Yeah, so it might be jump off from some of the development that we are doing. So maybe let's start with this page. So one of the first things that we are implementing is a WebAssembly state machine, or in general WebAssembly execution environment. And you can already run with Parity, a chain that uses WebAssembly rather than EVM. It's pretty good because it's performant, much more performant than EVM, so we can pretty much perform computation and like almost native speed. And it will keep on being improved as the time goes on. So we can actually perform some pretty heavy logic in WASP. So actually, the state validation logic for all those that I was describing, all those different state validation logics, will have to be encoded as WASP programs that are then put on the relay chain. So we don't need to code up any of the, like, of course, we will code up validation logic for at least few types of chains. But then if someone wants to write a new chain, then they just write a new validation, state transition validation program that compiles to WASP and then put it on there. And then anyone can execute it without knowing anything about it ahead of time. They kind of get it and run it on their own. So it's not like a contract, really. It's just like a piece of code that everyone knows how to run exactly and runs the same way. So it's, for instance, in our case, it's very easy because you can already compile Rust, so the programming language that we write our client in, to WebAssembly, which makes it possible. We already have state validation logic for Ethereum, for instance, because our client runs the Ethereum, can run the Ethereum chain. So we just compile this piece of code rather than natively to WASM, and then we can put it on the blockchain and then let anyone run it, and they can validate the Ethereum chain. So this is a cool project, and as I said, then people can start writing contracts not only in Solidity or any languages that compile to EVM, but can start writing smart contracts in any of the existing languages that people have been writing programs in. Of course, probably favor languages that don't have very heavy runtime. So maybe Java would be pretty hard with garbage collection and everything, but definitely something like Rust is a pretty good candidate. And then what we'll also introduce in order to make it much more speedy for smart contracts is split up the concerns how we meter the computation. So right now in Ethereum, every operation is metered in gas, and regardless if it's consuming CPU or it's doing I/O or it's using some memory. So in this case, there will be kind of 3 dimensions to each operation. So which will make it possible to get kind of much closer to the limits of a particular machine, because it's just not the lowest denominator, but which was, for instance, problem with the attacks last year with the Exp code, because it was consuming much more of one particular resource than all the other ones. So that's chromatic gas. So then we are we are working on a number of different components in order to make the Polkadot work. And of course, a lot of them are now pretty low level, and it will be probably for a while hard to actually get in there and use all the stuff. But hopefully later on we'll get to kind of higher levels and make nice IDs and things like that will actually make it easy to develop on all of it. But one thing is the proof-of-stake consensus. So already in Parity, since a while ago, you could run chains with different types of consensus. So you can run it with the proof-of-work consensus, but there are also different proof-of-authority consensus engines. So now, and they use something called the validator set, which is basically, one part of consensus, you could say, is the logic according to which validators have to communicate with each other in order to arrive at a particular chain. And the other part is who are those people that are actually arriving at the consensus. So that's the validator set. So in a consortium, this might be determined by a majority vote. Maybe majority of banks say that other bank should join the consortium, then they join the consortium. If the majority votes for them to leave, then they leave the consortium. But in public network, we kind of don't really have easy identities, so we have to rely on something like stake. So in this case, who contributes more stake to the network, who ties up more more value is able to join as part of the validator set, and who doesn't then cannot. Writing those contracts, so making sure that we can actually produce full light client proofs, so not only kind of small proofs of very particular bits and pieces within the EVM, but making sure that actually we can have a validator that is completely separate from a collator, where collator gathers up those transactions and produces a full light client proof to the validator, and validator can take it and run it. And of course, the next task will be to actually separating those two and then making them communicate over a network rather than just doing it within a single node. Another thing that is a beginning of bridging to different chains is bridging chains with either of our validator set consensus engines to Ethereum or to any other chain. So this is already in one of our available in one of our repos. So it would, for instance, if there is, maybe you heard about the Czaban chain and it uses one of our validator set consensus engines, it would make it possible to, for instance, hold actual Ether from the public Ethereum network on that different chain. Because the bridge is managed basically by the authorities of that particular chain, or stakers, validators of that particular chain, and it enables relaying of transactions. So this doesn't enable pooled security, but it already enables the trust-free transactions to be relayed across different chains. Yeah.
How do you make sure the data is relayed and it's not tampered with and it's delivered in a timely manner so it doesn't slow down all the other states that depend on like one particular part?
Yeah, so in this case, just bridging is problematic. So in terms of like if it's correct data, so this is done by the consensus amongst all the validators that are running a particular chain. So you would have to have majority of those validators be malicious in order for some invalid data to be relayed. So that's how that part is handled. But in general, bridging is problematic. For instance, let's say if we would bridge to an Ethereum chain. So Ethereum chain, the transactions are not finalized straight away. They can be reverted. There can be reorganizations of a chain. So we need to ensure that only transactions that are finalized or messages that are finalized are relayed. So you have to basically wait for a number of confirmations like an exchange, or wait for the kind of hybrid Casper that will enable you to have finality, actual finality, and just relay it after finality. But in case of chains that are actual parachains in Polkadot, it would be possible to relay messages straight away because the consensus is done at the same moment across all of them. So you can be sure that if they are reverted or anything is changed, then it will be changed in tandem. It won't be like one chain does something else. You are sure that. Yeah, in case of Polkadot, the messages can be relayed straight away, basically on every block, and on next block you already have it available to trigger some state transition, and then, yeah.
But those would have to be on chains that implement Polkadot extension, right?
So there are different types. So the like full parachains, you know, they natively will work on a relay chain, and that like it just works out of the box. For existing chains, yes, there has to be a bridge built that will enable this interaction. So there can be multiple bridges built, and it depends on what this other chain is. So if it's depends in what direction it goes. So like if it's from a proof of authority network or another proof of stake network, then it can be handled by the validators of that particular network. Okay.
Would it be in the form of like an oracle on some chains?
It might be. So it's really up to a particular chain. So it's the best if it's a full like validator set chain with a validator set, because then you can basically the messages are as trustworthy as the whole consensus of that particular chain. right? Because if majority validators are good, then the messages will be good, and the consensus is good on that chain. Yeah. So like something like Cosmos-based chains or like Tendermint chains, then messages can be relayed from those with the same security as the state transitions of that particular chain are. So you cannot get any more secure. Yep.
I was thinking about the use of smart contracts and perhaps having two people paying on different parachains, and then once both are verified, a smart contract can then execute. So, follow, yes.
Yeah.
So, well, what about if you wanted two people paying for a service, but they actually want it on the same chain, but you just want to use Polkadot to verify the payments from the two separate people? Could you do that?
Two separate people on one parachain?
Yeah, it's on one chain, so you don't
Yeah.
really.
Yeah, then just runs like on a normal like Ethereum chain. So you mean like a smart contract, and it has like two people have to approve some transfer to be made. So it just runs like a regular Ethereum smart contract then if it's on a single chain.
Okay. So say they want to split the payment, like.
Yeah.
Like there's something that costs $100. One person pays 50, the other pays 50.
Yeah.
But the smart contract doesn't execute until all $100 have been paid.
Yeah.
They pay at separate times. It can be used for that.
Yeah, absolutely. So then it works like on Ethereum. So then first person would pay in at some point, then it would change the state of that particular parachain. Then you would wait a little bit, and then the other person can pay in and trigger the transfer. Another thing is now there is a lot of kind of data needs to flow around the network to appropriate parties. There is many more parties that the data needs to flow between, and it's different types of data. So we'll need to kind of improve how the data is able to be routed. So we are implementing the libp2p protocol. So this is what IPFS runs on, which is a more general than devp2p. devp2p can run on top of libp2p as well, but it will make it easier to design those different network topologies. State machine was state machine, and of course generalizing over different state machines. So making sure that a single node can just take the different state transition logic and then run it regardless and switch between them easily. So make it generic over state machines, and a number of different things. Hopefully things like, for instance, a bridge between consortium chains and public chains would be pretty useful pretty soon. So with Parity, we develop, for instance, solutions for energy companies or pharma companies where they have their own consortium chain, but at the same time, they would want to, for instance, use a collateralized token from the Ethereum mainnet. So maybe like there are already like dollar tokens on Ethereum or some other tokens, and they want to use it on their chain, but at the same, because they don't want to handle issuing their new tokens. So now they could, using a bridge, run their own chain that has appropriate fees for their particular application, but at the same time handle the dollars from the public Ethereum network. So bridging could be pretty useful, and especially if we make bridges also to new chains. So of course from Ethereum there will be a chain to a proof of authority or a proof of stake Parity chain, but then it could then go to some other chain that supports multi-sig, so something like Waves or maybe Bitcoin will make a fork with Schnorr signatures, and then you could make that as well. Yeah. And you can have a look at the progress of the project. So there is a bunch of repositories. Most of the work is by generalizing the Parity client. So if you're running it for Ethereum, a lot of the features will be coming into that. So it will make it will make it possible to do different things. There is a more technical chat and website. And there is also some information about the network itself. And there is also a Riot channel. So that's another kind of federated, slightly decentralized messaging service that a lot of crypto projects are switching to. Yeah, join us there.
So I have a kind of a scenario I was thinking about. So your client would, so the nominators, the validators, and what was the third one? The stakers or whatever?
Collators, nominators, validators, the main ones.
So all three of those have to run the same software that includes the Polkadot additions, correct?
Yeah. So actually, collators might be running slightly different software depending on the chain, but they could be running all the same. Yeah.
Okay. So the validators and the nominators, they have to run the client of the chain they're interested in or whatever on in order to communicate with the broader Polkadot network. Is that correct, or is there just a Polkadot client they can run and do that action without having specific?
So from a user perspective, how most users would run it, they would synchronize the relay chain, because the relay chain has all the canonical canonical sets for different parachains, and then if they are interested in particular information on a parachain, then they can get basically light client proofs for that particular parachain. So you could think of it as like relay chain and like different things hanging off of it that enable you to check different things. So if you want to check a balance or you want to send a transaction, then you would kind of just do the relay chain and then look up.
So the nominators, they choose from the list of everyone or from the list of anyone that's running the right amount of software to connect to?
Yeah, exactly. So someone needs to be kind of put themselves up, like I want to be a validator, and then based on their behavior, then they might be nominated or not nominated.
So they have to have the right version of the software that connects to the Polkadot network.
Yeah, but at the same time, a lot of so there are some things that I wasn't talking about. Basically, right now, even with the Parity Ethereum client, there is already a contract on the Ethereum network that says which version of the client is capable of processing which blocks on the Ethereum network. So if there is an upcoming hard fork, then we can, for instance, put on into the contract that older versions of our client will not be able to validate state beyond a certain block, and they have to upgrade themselves or just stop working. So then the nodes can then see that, and then they can stop, or they can like go out to the network and say, I want to upgrade myself because I'm not consensus capable. So we'll be putting much more stuff like that into the state machine itself, so that then the software doesn't need to change that much. So it will be hopefully a very thin shell that only enables network messaging and kind of some basic things, while most of the kind of logic that evolves will be inside of the state machine.
So that can be integrated into Geth so that everyone can have the software, so that not only the people running Parity have access to being validators on the entire Ethereum network.
So on the Ethereum, Ethereum network will stay Ethereum network, like unless there are different projects that want to, for instance, take the state of the Ethereum network and put it on a separate chain that will be working in a slightly different way. But Ethereum network will remain Ethereum network, and probably the way Ethereum network is validated by Geth and Parity will remain somewhat the same. So what changes if you want to become a Polkadot validator, then that requires quite substantial changes. If you know, there are teams that are very willing to also build an alternative client to the one we are building, but yeah, we're conforming with the Polkadot protocol.
Let's take, you can take that conversation out.
Oh, okay, sorry.
One more quick question.
Yeah.
And we'll let break.
Sounds good. So in general, there is a number of different components that have to be built. As the time goes on, we'll be releasing them as soon as possible, especially the functional components that everything is being developed in the open. But yeah, it's a big project, and the kind of the approximately that's the timeline, but we'll see how it will go.
Could you talk a little more about the rewards?
What do you mean? What for different parties in the system, or?
You said that there would be a reward for the validators and the other one.
Yeah. So basically, it's in this kind of proof of stake system. It's important to first of all be able to punish parties that do not conform to the protocol. So maybe they are kind of pretending to one person that one version of the chain